Yeah, that's why we have probability rules. Here we're gonna use coin, and using that one, any coin tossed, we have two possibilities. And that is one is head and the other side is tail. What this means, chances 1 out of 2 for each one. So for each one, for head and here is tail, chance is 1. The next part is empirical probability and classical probability. Here we have a definition for these two. The first one, empirical probabilities are determined by making observations. So here on this part we have observations and also we gather data. But on the other hand, classical probabilities are determined by reasoning. So reasoning mathematically. So we have these two here. Now let's work on example number 1 and apply these two on this part. Example number 1, flip a coin 10 times. Here we have 10 times and record head or tails. Calculate both the empirical probabilities you find in your experiment of flipping heads and then calculate the classical probability. So we have we should flip this one 10 times and record head or tails. So let's say on the first try we had head, second try again head, tail, head, we have head again, okay, so this one tail, let's have these two tail, and here head. Okay, so first I want to find what the empirical is. Okay, and based on that, we need to find probability you find. Okay, here is probability you find in your experiment of flipping heads. We need to find probability of head. And that is equal to number of heads is on top and denominator number of flips, which is equal to 10. So counting how many heads we have here on top based on these observations that we have, 1, 2, 3, 4, 5, 6, and in total we have 10. That is 0.6. So this was based on empirical probability, and now classical. So probability of heads is equal to, again, number of heads on the coin. So here we had these data based on our observations, but this one, the classical, is based on what we have here on top, that when we use a coin, we are gonna have two possibility, and that is one head, the other one is tail. Having the chance for each one is 1 out of 2 for each one. So we're gonna use that one on top for this part. Here is number of head on the coin, and denominator, number of possible outcomes. That is equal to, for each one, chance is 1, and in total how many possibilities we have is 2. So that is 1 over 2, and that is 0.5. Now next part is sample space, showing with S of a probability experiment is a collection of, so that is collection of all possible outcomes. So what I used here in denominator, that is actually our sample space. And what event is any collection of outcomes from a probability experiment. So an event consists of one outcome or more than one outcome. We will denote events with one outcome, sometimes called simple events. So we may use simple events. And we're going to use E for this part and S for sample space. And what this P of E is, this is probability of this event. So this E is our event, and that P is probability of that event. Okay, here is what we have for this part. Now on this box we have rules of probabilities. The point is that the probability of each event should be between 0 and 1, and also when we add all those probabilities, sum should be equal to 1. So the probability of any event, E, for example E, probability of that event must be greater than or equal to 0 and less than or equal to 1. So we have this part. The number 2, the sum of probabilities of all outcomes. So how many outcomes we have in one sample space? So all those outcomes, the probability of those outcomes must be equal to 1. So see, here I have E1. What that is, this is the first event we have, second event, and up to here we have nth event. So probability of each one, finding that, adding all these, the answer should be equal to 1. So we should have both number 1 and 2 to have this rule for probability. This is equal to 1, or you can say, in other words, that is equal to 100%. And each one of these are event. Now, a probability model lists the possible outcomes of a probability experiment and each outcome probability. If an event is impossible, so if that is impossible, what that means, the probability of the event is 0. This means probability of event is equal to 0. So this is impossible. If an event is certain to occur, the probability of the event is 1. So what that is, this part is probability of E is equal to 1 or 100%. So we are 100% sure that we're gonna have this event. That is our probability for having this event. Next one is an unusual event. This is an event that has a low probability of occurring. So, and what that is, an event with a probability less than 5%. So if you had this, for example, probability of this event, this was less than 5%, then this is unusual event. So here we have unusual event. Now, example, verify that the following is a probability model. What that means, we should have these two rules. I should have the first and second rule together. If I don't have one of these, for example, if I had the number 1 but not number 2, and vice versa, that means that we don't have this probability model. Now, based on this table, the second column here is probability. That is, let's use, for that one is, let's use R. Here, G, B, for that one, BR, because that one also is B, Y, and O. You don't need to write like that, but since I want to explain that these are probability, what that means, so probability of red is equal to 0.3, and this is between 0 and 1. So obviously this number is between 0 and 1, so we satisfy the first rule. Now, second one, probability of green is equal to 0.15. This is again between 0 and 1. So that is correct again. Now, probability of blue is equal to 0. And here again, this is between 1 and 0, because this is equal to 0. That's why that is correct. Now, probability of brown is again 0.15. So it's between 1 and 0. Here, yellow is 0.2. Here again is between. And finally, probability of orange is again 0.2, is between 0 and 1. So all of these probabilities are between 0 and 1. So between 0, 1, meaning that we satisfy the first rule. And what is the second rule? Is that we should add all these numbers and that should be equal to 1. And this is equal to 1. And you try to add them. So this was the first one. Now here is second rule. Adding all these probability of R, G, brown, blue, brown, yellow, and orange. So adding all these. So I'm writing these numbers. Okay, let's use semicolon. So this is equal to 1. What this means, based on the first and second rule, we have probability model. So here rule 1 and rule 2 are satisfied. And also here we have probability of blue is equal to 0. So this one is impossible event. So this is impossible. And that is because its probability is 0. Now in this part, we should compute and interpret probabilities using the empirical and classical methods. The first one is using empirical approach. What we have here is exactly the same as on the previous chapters. If you remember, we had relative frequency, and that was based on our frequency for each event. And also we should find denominator, we should find sum of frequencies. So here we have same thing. Probability of this event is approximately equal to relative frequency of that event, and that is equal to, on top, frequency for each event divided by number of trials of experiment, which is exactly the same as having sum of the frequencies. So this is event E. Now here on this part we have classical method. And for the support probability of this event, on top we have number of ways that we can have E, and denominator is number of possible outcomes. Meaning is the same, but we have different words here. So this is probability of event, and that is equal to number of ways that we can have this event, and denominator is number of possible outcomes. So this is because we have number, that's why we use n. Exactly same as this one. This is P for probability, and here is event. Okay, so this is number of outcomes, and that is in sample space. So I don't want to write outcome here, so you may think that that is our outcome, or so it's number of outcomes inside that sample. Now, example, the data in the table represent the results of a survey in which 200 people were asked their means of travel to work. So in this table we have frequency for each group. Part A used the survey data to build a probability model for means of travel to work. Okay, so here I'm going to use this this table, and for part A, change to relative frequency. So change relative frequency. I'm writing the output here. So here in total we have 200. And each one divided by 200. So for the first part, I'm running to 3 decimal places. So the first one is 0.765. Here 22 divided by 200 is 0.11. This one I have 5%, 0.025, 0.015, and finally 0.035. So this is what I got for part A. So as you can see, all of these are, so these are probability. Each one of these are between 0 and 1. And also, if you add them, you're going to have approximately equal to 1. Okay, what that means, we have probability model. Now, part B, estimate the probability that the randomly selected individual couples to work. So now part B, probability. Here we have probability that the randomly selected individual couples. I'm going to use probability couples. And based on this table here, we have, like this is carpool. This is what I have for probability. So these are, in other words, this column is what I have for probability. So once again, each one of these are between 0 and 1, and add all of these numbers. This should be equal to 1 or very close to that. And why we say very close to that? That is because we round each number. That's why. Okay, so that is equal to 0.11 or 100%. So we should interpret this, what that means. This 0.11 is equal to 11 over 100, or we can also say 110 divided by 1000. I multiply by 10, each numerator denominator, to have this part. So we can say out of 1000 people, 110 are expected to carpool. Now, what is part C? Would it be unusual to randomly select an individual who walks to work? So is this one? And probability for that one is 0.025. So if our probability was less than 0.05 or 5%, we're gonna have unusual. And the answer for this part is yes. So because we have probability for that one is equal to 0.025, and this is less than 0.05. So yes, this one is unusual. Okay, so this one was an example for empirical. As you can see, we use frequency and relative frequency based on what we had on the first table. Now example number 4, a pair of fairy tires is rolled. Part A, computed probability of rolling an 8. So this is example of classical. This part is classical, and here we have 8. So asking to find probability of 8, and that is equal to number of 8 and here denominated number of outcomes. That is equal to, based on what we have here, we should see, do we have, how many 8s we have here? So how we can find which one is 8? Adding these two numbers, so 1 plus 6 is 7 here, 2 plus 6 is 8, 3 plus 6 is 9. And here on this part we have all these 5 events. Adding the first and second part, adding all these, we have 8. So 2 plus 6, 8, 3 plus 5, 8, 4 plus 4, 5 plus 3, 6 plus 2. All of these are equal to 8. So how many 8s we have is 5. And denominator number of outcomes in this sample space, so we have 1, 2, 3, 4, 5, 6 times 6, we have 36 in total. this is the answer for part A. Now part B, compute the probability of rolling snake eyes. That is, compute the probability of rolling 2. So this actually means of finding the probability of rolling 2. Exactly same as that part. Instead of 8, now we have 2. So number of 2 divided by number of outcomes. That is equal to, here we only have 1 for that part. So it's 1 divided by 36. Now part C, comment on the likelihood of rolling an 8 versus rolling a 2. So based on part A and B, since probability of 8 is 5 divided by 36 and probability of 2 is 1 over 36, we can say that it is 5 times more likely to roll an 8. See, this is equal to 5 multiplied by 1 over 36. So that's why this is 5. This one is 5 times of having probability of 2. So since probability of 8 is 5 divided by 36, and probability of 2 is 1 over 36. We can say that it is 5 times. Yeah, other example number 5. Let the sample space be, so this part we have all these natural numbers up to 10. Suppose the outcomes are equally likely. Compute the probability of the event, this event E. We only have 3 numbers, 1, 2, 3. And we should find what the probability of that event is. Obviously, number of digits that we have here divided by number of digits that we have in S in sample space. So it's 3 over 10. So what that is, this actually means find a probability of selecting one or 2 or 3. The probability of this event is equal to how many numbers we have here is 3, and how many we have here in for our outcomes is 10. So number of outcomes in this sample space is 10. The answer is 0.3. Now next one, compute the probability of the event. So this event we have 4 numbers inside. Probability of F. So same thing. Count how many numbers you have is 4. And in total, how many outcomes we have here in this sample? We have 10. So that is 0.4. Now part C, compute the probability of the event E, and that is an even number less than 9. Rewriting that part. in roster form. So we have even number 2, 4, 6, 8. I'm not able to write 10 because it's less than 9. So we should stop here. Now probability of this event is equal to how many numbers we have here inside, is 4, divided by, again our sample space is that one, so we have 10. So exactly same answer as the previous part. We have 0.4. Now part D computes the probability of the event F, and here is odd. So we have odd number. It's 1, 3, 5, 7, 9. We stop here because here our sample space is up to 10. I don't have, after that, I don't have 11, 13, so I'm not able to continue on this part. So we should stop here. Now, probability of this event. When we say event, that doesn't mean we always should use E. So here in this case, I have F. Our event is showing with F. So that is equal to how many numbers we have here inside, 5, divided by how many numbers we had here in our sample space is 10. So it's 0.5. Now, what we have here on number 6, according to the U.S. Department of Education, 42.8% of the of 3-year-olds are enrolled in daycare. What is the probability that the randomly selected 3-year-old is enrolled in daycare? So this is really easy to answer because we already have the answer here. The answer is given, is here in this part, because 42.8% of 3-year-olds are enrolled, and it's asking what is the probability that the randomly selected 3-year-old is enrolled. It's already given, so this much are enrolled. And let's use this one for this. So what is the probability? I don't want to use percent. Instead, I want to use this one. So I change that number to a decimal. And that means probability of 3-year-old enrolled in daycare is equal to, we have 0.428. So this is our probability for this word. Okay, I finished this section.